How would you like to follow 007? Bond, James Bond. What is all these cables for? Okay. There's been a whole lot of discussion and kind of emphasis on simulation. So I'm going to continue that sort of thought with simulation, not from a virtual reality, real time, but using simulation to try to improve safety as well as the design. The virtual testing validation method starts with coupons. It's a physics first type thing. The first thing you do is you step up, you do a step-by-step development of material properties, material constitutive properties, developing the properties you need for the fuel bladder, as well as the interconnect tubes, the composite or the material structure around it. All of those different constituent properties need to be developed first, and you do that on you develop the property and you do test it. Here I've got shown the puncture test with a screwdriver poking through the finite element model. This is an LS Dyna model. Develop the puncture capability, the tensile stress, the trouser tear, and so on. All of those different individual tests develop the material characteristics. Then you build those together and you do a component test. Here, the second one up I'm showing is the fuel drop, a bare bag drop test, where you evaluate both the fluid structure interaction, the material properties, the damage properties, how the seams bond together, and so on like that. And then finally, you develop that into a systems approach where you look at the full system, the full structure interaction, and this monitor just went off. The full system interaction with the fluid structure interaction, the structure, and so on, see if it works. So that's the step-by-step process you would go through as you develop the virtual testing methodology. One of the examples I want to pull up, and I'm going to be showing you three different helicopters that we've done a fuel system modeling with, the 429, the 505, and the 525. In 2009, we wrote a paper, Samgeeth Rajan, Dr. Tho, and me and I wrote a paper at a AHS forum, and this is some of the documented results of that. There was a pressure transducers we put in there, accelerometers we stretched over that. The paper documents all of them, but these are just 4 of them at the end. The test was the blue and the simulation is the red. But the overall impulse energy, the integrated area under the curve, has a good agreement, as well as the peaks, the peak loads, peak pressures we use size for. So this was a decade ago. Remember, if you're doing a paper presented in May of, you're writing that paper about now, 10 years ago. So this has been a decade. We put that together and demonstrated very good agreement at that point. So as we move forward, and this somehow or another didn't translate, but we're going to get it going there. You can click all of them, all 3 of them. This is actually the 505 drop test, the full system with fluid in there, the 80% full of water and so on. And the pre-test predictions are on the right. Phenomenological agreement is very good. Macro-mechanical response, you can see agreed. But in the lower right-hand side, you'll see the, oops, go back. That lower right-hand side, yeah, turn that on. You'll see, watch that, the fuel probe that's go down, that you can see in there, let's click it again, compresses against the bottom and buckles, and next slide shows the results of that. The fuel quantity probe buckled, and it caused deformation of the flange, and all of that was everything you're looking at is there any potential risk in leakage? That's the biggest thing you're looking for in a fuel system drop test. And sure enough, to show that by analysis, if you're looking at analyzing these, you're looking at this is a chain, it's a system. It's like the weakest link in the chain. If that fails, your whole system fails. And so you're trying to track through all of those components and see if you can find out where it did fail. And sure enough, that's the one area that the analysis pre-test predicted. In that sense, pre-test, before you see the results of the test, your analysis is out, and you say, yeah, it does agree. So that was another case where the analysis was very effective at guiding at predicting the results. And now let's take a look at the 525. This is a bare tank drop where you drop it and see if the tank holds up, and the two simulations below, both the fluid transparent in the structure, in the tank, and then the tank itself. Do we have to click those, or? So this is a 50-foot drop. It's 15.2 meter drop. And again, in this case, this does not meet the 952 criteria of having the structure surrounding it so that it busts up and creates puncture threats. So can you go ahead and click those two? Never mind, we don't have. So, oh, there they go. Well, I think you got the point. Okay, now you're going to see it too. So the fluid, both the rebound, and then as the stress wave and that fluid goes down and starts to move back up, you start having the rebound effect, and the response matched well with the structure. So this is the 525 test specimen. It's a section out of the 525. It contains 7 tanks interconnected through structure. And when you do the drop test, you fill all the tanks up 80% full of water. Now, if you have a basic hydrology understanding, you'd recognize that when you fill those higher tanks, their head pressure is a little bit above, and they're going to drain down into the lower tanks, right? You can't do that. That under-tests the back tanks and over-tests the lower elevation tests. So you really have to seal off those interconnects. Well, it's important, a couple of things. First, when these interconnect tanks, when the interconnects go through structure, you have the potential risk of a guillotine effect, where the tank, when it deforms down, can hyperstretch the interconnects, or the structure can actually close off or become a risk there. So just because you've sealed it, you need to make sure you also evaluate, is there any risk of failure of those interconnects? In fact, the fluid is still there, it's just blocked, and if it leaks on either side, you're going to still have leakage. So you have to check that, make sure that you still have a complete system that will not introduce failure risk. So this is a view of it. It's important first as you go through these, we go back, when we look at the full system, you have to remember that it first started with fundamental physics. You've got to go back and make sure that material character, the constitutive properties of the material, and all the design aspects are carefully built up, because it's a building block approach. You build from the basic physics of the materials, go up into the component, and then you do the full system. By doing that, you have a virtual testing system or method that can help guide the design. Your first design may or may not work, but you don't want to go test it and find that out. By definition, a certification test necessarily occurs late in the design cycle. Does that make sense? You want to test the certification, the type design that's going to be certificated. That usually occurs pretty late in the cycle. And if you have a failure at this point, it's not only costly in terms of having to repeat the design, go through the whole design, go back and refabricate and go back and retest, you have a huge impact on delay to market. And so missing that is massive. So virtual testing offers you a strong increase in confidence in first pass success on your certification test. Really, from a safety perspective, that's the standard, the bar. 952 sets the bar. You're going to meet that. You're not going to be more or less safe. You're going to meet the criteria, the bar, okay? But getting there is important because you want to work out all the failure mechanisms, all the problems in the design as you're moving forward. And I can be honest, our first design was not our final design. And so as we walked through that, there were some improvements that we made. First of all, the structure needs to maintain integrity. If the structure disintegrates, you introduce additional failure mechanisms that threatens the fuel system, fluid containment. So in this case, we found that we needed to add some doublers to keep the floor and the bulkhead together. We had to keep a doubler on the aft landing gear bulkhead because the hydrodynamic pressures are higher than the static or even the static loads of the regulatory. The static loads of regulatory requirements are nowhere near high enough to meet the dynamic requirements, hydrodynamic requirements. And you just might take note of that. The pressures you're looking at are you're not talking about as low as 100 PSI. You're talking about like 500 PSI type pulses on the bottom of the tank. Well, most of the designs are not going to be sized for 500 PSI static, nor should they be, because you won't be able to fly a helicopter. It'd be way too heavy, right? So you've got to run through this in a hydrodynamic type of environment where you size the pulse and the energy, and remember that going plastic is your friend. It absorbs energy. So in a crash environment, plastic energy is good as long as you don't fail, or if you do fail, it's designed to do that, designed and you handle those sort of failures. So one of the other things we discovered was that we needed to put reinforcement, Kevlar reinforcements over the bag areas where you had hot spots, if you will, the potential threat of puncture on the bags and things like that. So you work through the design using virtual testing to improve the design to meet the criteria to have the safety that you want for a crash-resistant fuel system. Statistics show that if you have a crash-resistant fuel system, you have a tremendously improved safe system for a crash, for survivability in a crash. Okay, so let's see. This is how the final system, we just finished up this last year. We did the test in February, but this was a pre-test prediction, and I just crashed it twice pre-test. But you can see that the floor stays together, the structure stays together, and so on. There's some cracking. You can see it in the forward bulkheads. Forward rings. You can see some cracking in there and so on. But that's fine. The system is evaluated. So let's see how the actual test goes. Now this is the actual test, and don't click it yet. It's fine. No, I'll click it. No, wait. No, okay. I'll click it. Okay. Okay, we're not quite up there at five floors up. We're halfway through the fall here, but this test is like rolling off this structure and pushing it off the top floor of the sixth floor, right? Sixth floor, so you're 5 floors below you, 50 feet or 15.2 meters. You push this big old, that's just like 2 or 3 Suburbans, welded together, and you're going to push it off onto concrete, and then you're going to pick it up, and you can't be leaking. You're going to turn it upside down, can't be leaking. It's a very challenging test, and if you've done it, if you haven't done it, you ought to have your jaw hitting the floor. But it works, and it's a very good design. It's just a test to prove this test. So let's see how this works. Now, you only have to drop it once, but I gave you the repeat shot for you for the effect. So I'm gonna do a slow motion. We're gonna pick up the slow motion and then sequence in the simulation with it, and I'll do it a second time here. All right. As you're coming down, notice how the floor is together. Okay. Now, one of the things I want to point out with you is that when you're doing that test, I think it's 3 times. When you're going through that test, what's happening to the fuel system inside? You don't know. Your camera can't tell you either. You don't know. But when you do a virtual testing, you know how that interaction, you know where the tank is, you know where the elastic lines are, you know how the tank is responding. And so you have so much more insight. You can go into every little passage, every little connection through the simulation that you can't when you do it in test. Now, granted, the test is real world, but in truth, it's kind of funny. The people that do testing and have a lot of experience with testing, they have a lot of confidence in the analysis. They really do, because they recognize test is fraught with test error and can have some problems with it. And they go back and say, well, what does the analysis say? They have a lot of confidence with that. The lesser experienced people who don't have as much experience with testing tend to think, well, that's real world data. That's test world. That's real world data. And they don't recognize how shallow of an understanding those words are. That if you just relying on test without analysis, you're going to put too much trust in your test data. You recognize you may have all sorts of problems in a test, and you got to recognize that. The two of them go hand in hand to provide the very best of the solution. Okay, in 2009, there was an AHS paper by Charles. Let's see, it was Scott Harris and Charles Shepard, and run to my notes so I get the title right. Called Strategic Research Planning and Management. They set up a 9-level tier for analytical readiness level, and analytical tool readiness level is what the U.S. Army calls it in their full spectrum crashworthiness specification. So the 9 levels here are written down. When we started this work off, it was at a level 5 a decade ago, back in 2009 when we did that. That was predicts trends reliable enough to discriminate between designs, good qualitative trades possible after calibration. Now, I mentioned this scale. This is patterned after the technology readiness levels, and there's also a manufacturing readiness level criteria that the U.S. military and NASA use, and I don't know how prolific it is outside of that, but they use that very extensively, the TRLs. This is an ATRL, the Analytical Tool Readiness Level, that scales with that. You might think, it's not just a Boolean algebra, a binary thing on-off. When you're moving to certify by analysis, it's not yes or no, it's a spectrum. How far are you? And you need to manage to that spectrum, and this is a way of looking at that from that perspective. The gold star down at the bottom is where you do the analysis, and by golly, you certify from that, okay? But somewhere in there, we need to move. Well, the work that we've done since 2009 has moved that bar down from 5 down to 7 at least. Process predicts absolute value, no development testing is required, quantitative trades possible. There was no development testing in that sense of system testing. We didn't drop that system beforehand. We had high confidence that it would pass. Now, these guys over here, I know the pucker factor was big when they were sitting there ready to push that thing. Their palms were sweating and things, but the guys who did the analysis were calm. We knew it was going to work. You laughing? Okay, and we had high confidence. Let me move on, and I'm going to. But there's also, it's arguable that we are at a level 8. Process predicts absolute value, certification quality, qualification authorities accept analytical results with reduced testing. The only difference between 8 and 9 is the word reduced, okay? Let me point one thing. In the area of Birdstrike, we do the same sort of thing with Birdstrike Prediction. Martin will remember we did a test once where a tail rotor, we predicted a tail rotor would pass. We didn't build it, it was somebody else who built it. And And so we go down there and watch. We were all ready to have it test, and that bird went right into that tail rotor and just blew the whole tail rotor off. I mean, it was a complete dramatic failure. We scratched our heads and thought, something's wrong with the test because the analysis is right. Now, that's arrogant to think that, but we were right. There was something wrong with the test, and sure enough, when you go in there and you look, the material properties were wrong. The resin properties there was resin starvation in there. The composite, it wasn't per wasn't per the drawing. I mean, there's a conformity error there. The test article did not match up with the test design part. The design was what we analyzed. It would have passed. So we reanalyzed the system with the reduced properties, material properties. Remember I told you it starts with physics first, get your material properties right, and voila, completely replicated what we saw in the test with the dramatic failure. That to me was one of the strongest cases for the fact that analysis, we nailed it. And you can have high confidence when you're at that level, when you're at a ATRL level of 7 or 8, you have high confidence that the analysis is right, and you dig back in and you find out some problem with the test, okay? So I want to just say that this approach for somehow I'm not advancing. There we go. The virtual testing approach that we've been talking about is at a mature level. We've demonstrated it on 3 different platforms, the 429, the 505, and the 525, different designs, different approaches, but validated pre-test predictions. But by using that method, you're able to improve the design and improve your confidence level going into a test that you're going to pass. And that's really key and important. So the ultimate objective, what we're after, is to certify by analysis, okay? And that there is an AC out there that does that, so it's analogous to the AC that's written for seat testing, for modeling human body dynamics in a seat and evaluating that from an analytical perspective. Analogous to that, we're talking about doing that for drop tests, for fuel system drop tests. So we think that the technology has arrived and we're ready to start looking at moving that way. And we'll save the questions for later. And so I believe you still have your extra 10 minutes, Martin.